Good day to the class of Bachelor of Science in Civil Engineering. After we have learned the soil engineering for highway design and the bituminous materials, we are now going to jump into the next subtopic under the scope of pavement materials and design. Thus, for this video presentation, we are going to talk about the highway pavements. But the central point of this video presentation only revolves around the first type of highway pavement, which is the highway flexible pavement. Also, it is specifically focused on its design and the calculation as well. So without further ado, let's start our discussion. And by the way, I am Kenneth the Infeliz, and I am going to be your discussant for this particular topic. Now, let's take a look at the overview of the topic. As you can see, this topic has three categories, and it begins with the structural components of a flexible pavement. In here, we're going to talk about the composition of highway flexible pavement, what flexible pavement is composed of, the differences of these components, and how they are being layered on the ground. For the second one, we have the soil stabilization. Not being a spoiler, but there are numbers of methods for us to stabilize the soil, and we're going to talk about that later as well. And last but not the least, we will be ended up with the general principle of flexible pavement design, in which it will help us to be able to design and calculate the flexible pavement that we're going to lay. And in here, we're gonna appreciate the different method to identify the loads, such as the traffic loads, in order for us to design a more safer and economical flexible pavements. Before we'll go to the flexible pavement, let's define first the highway pavement. So highway pavements are constructed of either asphalt or concrete, and ultimately rests on native soil. As you can see on the screen, that are the example of highway pavements. They're just basically the road, in other words. So highway pavement is divided into two main categories. The first one is the flexible pavement, which is our central focus, and it was being defined as the one usually constructed of bituminous materials. Secondly, we have rigid pavements, usually constructed of Portland cement concrete. Now, let's formally go to the specific. So, flexible pavements usually consist of a bituminous surface underlaid with a layer of granular material and a layer of a suitable mixture of coarse and fine materials. Traffic loads are transferred by the wearing surface to the underlying support materials through the interlockings of aggregates, the frictional effect of granular materials, and the cohesion of fine materials. So, as being said earlier, these flexible pavements are those which are surfaced with bituminous or asphalt materials. In Tagalog, ito po yung kalsada na may asfalto sa ibabaw. These types of pavements are called flexible since the total pavement structure bends or deflects due to the traffic loads. So, for example, the flexible pavement is basically look like this picture. Furthermore, the flexible pavement is divided into three subgroups. The first one is the high type pavement. It has wearing surfaces that adequately support the expected traffic load without visible distress due to fatigue and are not susceptible to weather conditions. Secondly, the intermediate type. It has wearing surfaces that range from surface treated to those with qualities just below that of high type pavements. And the last one is the low type pavements that are used mainly for low-cost roads and have wearing surfaces that range from untreated to loose natural materials to surface-treated earth. So for this report, we're going to deal with the design of a new high-type pavements although the methodologies presented also can be used for some intermediate type pavements. Now, let's begin with the first subtopic, the structural components of a flexible pavement. So the first component is the subgrade, which is also known as the prepared road bed. So the subgrade is usually the natural material located along the horizontal alignment of the pavement and serve as the foundation of the pavement structure. So on that screen, you can see that the subgrade is the innermost part of a flexible pavement, right below the sub-base course, which is the second component that located immediately above the subgrade. The sub-base component consists of materials of a superior quality to that which is generally used for subgrade construction. The requirements for sub-base materials usually are given in terms of gradation, plastic characteristic, and strength. The third structural component is the base course. The base course lies immediately above the sub-base. It is placed immediately above the subgrade if a sub-base course is not used. This course usually consists of granular materials such as crushed stone, crushed or uncrushed slag, crushed or uncrushed gravel, and sand. The last one is the surface course. The surface course is the upper course of the road pavement and is constructed immediately above the base course. The surface course in flexible pavements usually consists of a mixture of mineral aggregates and asphalts. It should be capable of withstanding high tire pressures, resisting abrasive force due to traffic, providing a skid-resistant driving surface, and preventing the penetration of surface water into the underlying layers. The thickness of the wearing surface can vary from 3 inches to more than 6 inches depending on the expected traffic on the pavement. We're done with the structural components of flexible pavements. That means that the soil stabilization is now taking a place. Let's go directly to the definition of soil stabilization. The soil stabilization is the treatment of natural soil to improve its engineering properties. It is the alteration of soils to enhance their physical properties. The stabilization can increase the strength of a soil and or control the shrink and swell properties of a soil, thus improving the load-bearing capacity of a subgrade to support pavements and foundations. These pictures are some of the examples of soil stabilization. Soil stabilization methods can be divided into two categories, namely the mechanical and the chemical. The mechanical stabilization is just the blending of different grades of soil to obtain a required grade. In other words, mechanical stabilization is just the process of improving the properties of the soil by changing its gradation. However, we need to take note that the mixing or blending of soils of 2 or more gradation should be obtained by meeting the required specification. So the second one is the chemical stabilization. Chemical stabilization is the blending of natural soil with chemical agents. Several blending agents have been used to obtain different effects. So later on, I'll be also presenting a table that shows different chemical agents used for soil stabilization. But for now, the most common used agents are Portland cement, asphalt binders, and lime. It is necessary at this point to define some of the terms commonly used in the field of soil stabilization, particularly when Portland cement, lime, or asphalt is used. Later on, I will be discussing that. But for now, let's take a look at these pictures. These pictures are just the examples of mechanical and chemical stabilizations respectively. You can see that the mechanical one is just focused on the gradation of stones and gravel, etc., while the chemical one is for chemical agents put on the soil. As being mentioned earlier, this is the table showing the soil types and stabilization methods best suited for specific applications. Like for example, if we're gonna reduce the frost susceptibility of fine granular soil type, the recommended stabilization methods are CMS or cement modified soil, SA or soil asphalt, SC or soil cement, and LF or lime flash ash. So the definition of these terminologies is presented on the next slide. You can see all of that very shortly, but I want to emphasize that we should be guided accordingly with this table because this will help us to identify the best suited stabilization methods for specific soil types in order to have a safe and efficient road. So these are the some stabilization methods and their terminologies. I'm not gonna read this one by one because they're just self-explanatory and you can read and understand them as well as identify their purposes all by your self-effort. Now, let's move on to the soil stabilization in pavement structures. We have the cement stabilization. The cement stabilization of soils usually involves the addition of 5 to 14% Portland cement by volume of the compacted mixture to the soil being stabilized. This type of stabilization is used mainly to obtain the required engineering properties of soils that are to be used as base course materials. Under the cement stabilization, we have procedure to follow such as the pulverizing the soil, the mixing the required quantity of cement with the pulverized soil. The third one is the compacting the soil cement mixture and the curing the compacted layer. The next type of stabilization is the asphalt stabilization. The asphalt stabilization is carried out to achieve one or both the following. The first is the waterproofing of natural materials, in which asphalt stabilization aids in maintaining the water's content at a required level by providing a membrane that impedes the penetration of water, thereby reducing the effect of any surface water that may enter the soil when it is used as a base course. So the second one is the binding of natural materials. The binding of natural materials improves the durability characteristics of the natural soil by providing an adhesive characteristic whereby the soil particles adhere to each other, increasing cohesion. Another type of soil stabilization is the lime stabilization. Lime stabilization is one of the oldest processes of improving the engineering properties of soils and can be used for stabilizing both base and sub-base materials. In general, the oxide and hydroxides of calcium and magnesium are considered as lime, but the materials most commonly used for lime stabilization are calcium hydroxide and dolomite. However, we need to take note that the dolomite should not have more than 36% by weight of magnesium oxide to be acceptable as a stabilizing agent. For visualization, these are the fixtures of the said stabilizations in pavement structures. Now, we come to the last category, the general principle of flexible pavement design. So for the general principles of flexible pavement design, we have several design methods. The first design method is the American Association of State Highway and Transportation Officials, AASHTO design method. In designing the flexible pavement using the AASHTO design method, we have some design considerations to follow. The factors considered in the AASHTO procedure for the design of flexible pavement as presented in the 1993 guide are the pavement performance, the traffic or traffic load, roadbed soils or subgrade materials, materials of construction, the environment, the drainage, and the reliability. So for pavement performance, the primary factors considered under pavement performance are the structural and the functional performance of the pavement. The structural performance is related to the physical condition of the pavement with respect to the factors that have a negative impact on the capability of the pavement to carry the traffic load. These factors include cracking, faulting, rattling, and so forth. The second one is the functional performance, in which it is the indication of how effectively the pavement serves the user. The main factor considered under the functional performance is riding comfort. Recommended values for the terminal serviceability index are 2.5 or 3.0 for major highways and 2.0 for highways with a lower classification. In cases where economic constraints restrict capital expenditures for construction, the P sub D can be taken as 1.5 or the performance period may be reduced. However, this low value should be used only in special cases on selected classes of highways. The next design consideration following the pavement performance is the traffic load. In the AASHTO design method, the traffic load is determined in terms of the number of repetitions of an 18,000 pounds, or that is equivalent to 80 kilonewtons. Single axle load applied to the pavement on two sets of dual tires. This is usually referred to as the equivalent single axle load or the ESAL. The dual tires are represented as two circular plates, each 4.51 inches radius, spaced 3.57 inches apart. So later on, we're gonna have calculations about the ESAL. Now, we have here a table. This table 19.3a is showing the axle load equivalency factors for flexible pavement single axles and P sub D of 2.5. Note that this table only gives traffic equivalence factor for P sub D of 2.5 for single axles. So, the total ESAL applied on the highway during its design period can be determined only after the design period and the traffic growth factors are known. The design period is the number of years the pavement will effectively continue to carry the traffic load without requiring an overlay. The flexible highway pavements are usually designed for a 20-year period. Since traffic volume does not remain constant over the design period of the pavement, it is essential that the rate of growth can be determined and applied when calculating the total ESAL. The annual growth rates can be obtained from regional planning agencies or from state highway departments. These usually are based on the traffic volume counts over the several years. It also is advisable to determine annual growth rates separately for trucks and passenger vehicles, since these may be significantly different in some cases. The overall growth rate So, the growth factors G sub Rn for different growth rates and design periods can be obtained from equation G sub R of n is equals to the quantity of 1 plus R raised to n minus 1 all over R, where R is the I all over 100 and is not 0. If annual growth is 0, growth factor is just equal to the design period. The I is equals to the growth rate and N is equals to the design life, it's years. We have here again some tables. The table on the left side is for the axle load equivalency factors for the flexible pavement, tandem axles, and P sub T of 2.5. And another table right from the right side is the table for the growth factors. We will be using this table when we are calculating the ESAL later on. So as being said earlier, the table 19.4 shows calculated growth factors G sub R of N for different growth rates R and design periods N, which can be used to determine the total ESAL over the design period. So the portion of the total ESAL acting on the design lane, F of sub of D, is used in the determination for pavement thickness. Either lane of a two-lane highway can be considered as the design lane, whereas for multi-lane highways, the outside lane is considered. The identification of the design lane is important because in some cases, more trucks will travel in one direction than in the other, or trucks may travel heavily loaded in one direction and empty in other direction. Thus, it is necessary to determine the relevant proportion of trucks on the design lane. So, with that, we're gonna use a general equation for the accumulated ESAL for each category of axle load. So the general equation is given by the ESAL sub I is equal to F sub D times G sub R of N times AADT sub I times 365 times N sub I times F sub capital E sub capital E I, where ESAL sub I is equals to the equivalent accumulated 18,000 pounds or 80 kilonewton single axle load for the axle category I. The F sub D is the design lane factor. The G sub R of N is the growth factor for a given growth rates R and the design period N. Furthermore, the AADTI sub is the first year annual average daily traffic for axle category I. The N sub I is equals to the number of axles on each vehicle in category I. For FEI is equals to the load equivalency factor for the axle category I. Let's have a practice in computing the ESAL. So we have here a worded problem in computing the accumulated equivalent single axle load for a proposed 8-lane highway using load equivalency factors. So the given is something like this. An 8-lane divided highway is to be constructed on a new alignment. The traffic volume forecast indicate that the average annual daily traffic or AADT in both directions during the first year of operation will be 12,000 with the following vehicle mix and axle loads. So for passenger cars, 1,000 pounds per axle is equals to 50%. 2-axle single unit trucks, 6,000 pounds per axle is equals to 33%. The 3-axle single unit trucks, 10,000 pounds per axle is equals to 17%. The vehicle mix is expected to remain the same throughout the design life of the pavement. If the expected annual traffic growth rate is 4% for all vehicles, Determine the design ESAL given a design period of 20 years. The percent of traffic on the design lane is 45% and the pavement has a terminal serviceability index P sub D of 2.5 and SN of 5. So now, first we have to write the given data. So the growth factor is equals to the 29.78 from table 19.4 because the growth rate is 4% and the design period of 20 years. So the percent truck volume on design lane is equals to 45. The load equivalency factors from table 19.3 is the passenger car's 100 lb per axle is equals to 0.0002, negligible. The 2-point axle single unit trucks 6,000 pounds per axle is equals to 0.010, and the 3-axle single unit trucks 10,000 pounds per axle is equals to 0.088. So the solution, we're gonna use the equation for the ESAL. So the general equation is equal to the ESAL is equal to F sub D, or the design lane factor, times the G sub JT times AADT times 365 times N sub I times FE sub I. So let's continue the solution. So you notice that the passenger car's 100 pounds per axle is being neglected because the value is so low. So let's continue to the 2-axle single unit trucks. So to compute the ESAL for 2-axle single unit trucks, it is equal to 0.45 times 29.78 times 12,000 times the rate, which is 0.33, times the 365 times 2 times 0.010, that is equal to 0.3874 times 10 raised to 6. So for 3-axle single unit trucks, the ESAL will be equivalent to 0.45 times 29.78 times 12,000 times 0.17 times 365 times 3 times 0.0877 is equal to 2.6343 times 10 raised to 6. So these two, we're just gonna add this 2 and we'll get the total ESAL, which is equal to 3.0217 times 10 raised to 6. So the next procedure is the roadbed soils or the subgrade material. The 1993 AA SHTO guide also uses the resilient modulus of the soil to define its property. However, the method allows for the conversion of the Californian bearing rate or R value of the soil to an equivalent M sub R value using the following conversion factors. So we're gonna use the M sub R. The SI unit for M sub R is equals to pounds per inches squared, equal to 1,500 CBR for fine grained soils with soak CBR of 10 or less. Another one is modulus or resilient modulus is equals to 1,000 plus 555 R value for R plus 20. The next procedure is the materials of construction. The materials used for construction can be classified under the 3 general groups. Those used for the sub-base construction, those used for the base construction, and those used for the surface construction. The fifth procedure is the environment. Temperature and rainfall are the two main environmental factors used in evaluating pavement performance in the AASHTO method. The effects of temperature on asphalt pavement include stresses induced by thermal action, changes in the creep properties, and the effect of freezing and thawing of the subgrade soil. The effect of rainfall is due mainly to the penetration of the surface water into the underlying materials. If penetration occurs, the properties of the underlying materials may be altered significantly. Another one is the drainage. The effect of drainage on the performance of flexible pavements is considered in the 1993 guide with respect to the effect water has on the strength of the base materials and roadbed soil. The approach used is to provide for the rapid drainage of the pre-water non-capillary from the pavement structure by providing a suitable drainage layer and by modifying the structural layer coefficient. So for this procedure, we're going to use the table 19.5, the definition of drainage quality, and the table 19.6, the recommended Rn sub I values. Now, for the last procedure, we have reliability. So when it comes to reliability, it has been noted that the cumulative ESAL is an important input to any pavement design method. However, the determination of this input is usually based on assumed growth rates, which may not be accurate. Most design methods do not consider this uncertainty, but the 1993 AASTO guide proposes the use of reliability factor that considers the possible uncertainties in traffic prediction and performance prediction. Reliability design levels are percent, which determine assurance level that the pavement section designed using the procedure will survive for its design period, had been developed for different types of highway. For example, a 50% reliability design level. So, for example, a 50% reliability design level implies a 50% chance for successful pavement performance. That is, the probability of design performance success is 50%. The table 19.7 that was presented earlier on the last slide shows suggested reliability levels based on a survey of the AASTO Pavement Design Task Force. The reliability factors FR is greater than or equal to 1. Based on the reliability levels selected and the overall variations also have been developed, accounts for the chance variation in the traffic forecast and the chance variation in actual pavement performance for a given design period traffic. Now, in computing the reliability factor, FR is given as logarithmic of FR base 10 is equal to negative Z sub R times S sub O, where Z sub R is equals to the standard normal variate for a given reliability R%, and the S sub O is estimated overall standard deviation. So this standard deviation will get only from a table 19.8 presented also on this slide. In terms of the structural design for reliability, the objective of the design using the AASHTO method is to determine a flexible pavement structural number Sn adequate to carry the projected design ESAL. It is left to the designer to select the type of surface used when can be either asphalt or concrete, a single surface treatment or a double surface treatment. So this design procedure is used for EASL greater than 50,000 for the performance period. The design for ESAL less than this usually considered under low volume roads. The 1993 AASHTO guide gives the expression for SN as Sn is equals to A sub 1 d times d sub 1 plus A sub 2 times d sub 2 times m sub 2 plus A sub 3 times D sub 3 times M sub 3, where M sub 1 is the drainage coefficient for layer I, and the A sub 1, A sub 2, A sub 3 are the layer coefficients representative of surface, base, and sub-base cores respectively. The D sub 1, D sub 2, and D sub 3 is just the actual thickness in inches of surface, base, and sub-base courses respectively. Now, let's have another word problem. This time it's for designing a flexible pavement using the AASHTO method. So, the problem goes like this. A flexible pavement for an urban interstate highway is to be designed using the 1993 AASHTO guide procedure to carry a design ESAL of 2 times 10 raised to 9. It is estimated that takes about a week for water to be drained from within the pavement, and the pavement structure will be exposed to moisture levels approaching saturation for 30% of the time. The following additional information is available. So for the resilient modulus of asphalt concrete at 68° Fahrenheit is equals to 450,000 pounds per inch squared. The Californian bearing ratio value of base course materials is equals to 100. So M sub R, or the resilient modulus, is equals to 31,000 pounds per inch squared. The Californian bearing ratio value of sub-base course material is equal to 22. The resilient modulus is 13,500 pounds per square inch, and another CBR value of this time is for subgrade material, which is 6. And so the question is determine a suitable pavement structure. M sub R of subgrade is equals to 6 times 1,500 pounds per inch squared. So is equal to 9,000 pounds per inch squared. So the solution is just basically like this. So we're going to analyze first the problem. So since the pavement is to be designed for an interstate highway, the following assumptions are made. So for the reliability level, we have 99%. That is for the range 85 to 99.9 from the table 19.7. The standard deviation, we have 0.49. The range is 0.4 to 0.5. It is also from table for flexible pavement. Initial serviceability index, we have 4.5, and the terminal serviceability index, which is 2.5. So we have here a graph or a monograph. So this is for the design chart for flexible pavement based on using mean values for each input. So this monograph will be used later on for our solution. So here is the step-by-step process to accumulate the answer. So the monograph in figure 19.8 is used to determine the design SN through the following steps. So the step 1, we need to draw a line joining the reliability level of 99% and the overall standard deviation of 0.49 and extend this line to intersect the first T sub L line at point A. So step 2, we need to draw another line. This time is joining point A to the ESAL of 2 times 10 raised to 6 and extend this line to intersect the second T sub L line at point B. The next step, we're going to draw another line joining point B and resilient modulus of the roadbed soil and extend this line to intersect the design serviceability loss chart at point C. Step 4, another drawing, this time a horizontal line from point C to intersect the design serviceability loss or the change of PSI curve at point D. In this problem, the change of PSI is equals to 0.5 minus 2.5, which is equal to 2. So let's move on to the next step, step 5. We need to draw a vertical line to intersect the design SN and read this value. SN is equals to 4.4. Step 6, we need to determine the appropriate structure layer coefficient for each construction material. So for resilient value of asphalt, we have 450,000 pounds per inch squared. So from figure 19.5 is equal 9 A sub I is equals to 0.44. So for B, the Californian bearing ratio of base course material is 100. Also from figure 19.4, A sub 2 is equals to 0.14. So letter C, we have 22 for sub base and 8 sub 3 is 0.10. Step 7, we're going to determine the appropriate drainage coefficient. Since only one set of the condition is given for both the base and sub-base layer, the same value will be used for M sub 1 and M sub 2. The time required for water to drain from within pavement is just equal to 1 week. And from table 19.5, drainage quality is fair. The percentage of time pavement structure will be exposed to most moisture level approaching saturation is equals to 30. And from table 19.6, the M sub I is equals to 0.80. And last step, the step 8, we need to determine appropriate layer thicknesses from equation 19.6. So the equation is equals to A sub 1, D sub 1 plus A sub 2 times D sub 2 times M sub 2 plus A sub 3, D sub 3, M sub 3. Taking into consideration that a flexible pavement structure is a layered system, the determination of the different thicknesses should be carried out as indicated in figure 19.9. The required SN above the subgrade is first determined, and then the required SNs above the base and sub-base layers are determined using the appropriate strength of each layer. The minimum allowable thickness of each layer can then be determined using the differences of the computed SNs as shown in figure 19.9. Now we are close to find the answer. Using the appropriate values for M sub R, or the resilient modulus, in figure 19.8, we obtain Sn sub 3 is equals to 4.4 and Sn sub 2 is equals to 3.8. Note that when Sn is assumed to compute ESAL, the assumed and computed Sn sub 3 values must be approximately equal. If these are significantly different, the computation must be repeated with a new assumed Sn. So we know that the resilient modulus for base course is equals to 31,000 pounds per square inch. So using this value, we're gonna in figure 19.8 we obtain the S sub n is equals to 2.6. So giving 2D sub 1 is equals to 2.6 all over 0.44. So 2.6 divided 0.44 is 5.9 inches. So with that, using 6 inches for the thicknesses of the surface course, the D sub 1 is equals to 6 inches. The Sn sub 1 is equals to A sub 1 D sub 1. So we just substitute the values. So the A sub 1 is equals to 0.44 times the D sub 1, 6 inches. We will obtain 2.64. So for D sub 2 naman, it is greater than or equal to Sn sub 2 minus Sn sub 1 all over A sub 2 m squared, m sub 2. So 3.8 minus 2.64 all over 0.14 times 0.8. So the D sub 2 is greater than or equal 10.36 inches. So we're gonna use 12 inches. So the Sn sub 2 naman is equals to 0.14 times 0.8 times 12 plus 2.64. So that is all equal to 1.34 plus 2.64. So the D sub 3 is equals to Sn sub 3 minus Sn sub 2 all over A sub 3 times m sub 3. So the Sn sub 3 is equals to 4.4. We're gonna subtract that to 2.64 plus 1.34, the value of Sn sub 2 all over 0.1 times the m sub 3, which is 0.8, is equal to 5.25 inches. So we're going to use 6 inches for a safe pavement. So Sn sub 3 is equals to 2.64 plus 1.34 plus 6 times 0.8 times 0.1 is equals to 4.46. So the pavement will therefore consist of 6 inches asphalt concrete surface, 12 inches granular base, and 6 inches sub base. Another general principle of flexible pavement design is the Californian H-beam design method. So for Californian design method, the traffic load is initially calculated as the ESAL, as discussed earlier, that is the total number of 18,000 pounds axle loads in one direction, and then converted to a traffic index TI, where TI is equals to 9.0 times ESAL all over 10 raised to 6 raised to 0.0119. So in determining the ESAL, passenger vehicles and pickups are not considered. The strength of the subgrade material is given in terms of the resistance value R of the subgrade soil obtained from the H-beam stabilometer test described in chapter 17. So the strength characteristic of each construction material, asphalt, concrete, base, and sub-base material, are given in terms of gravel equivalent factor, which has been determined for the different types of materials, and the factors given for the asphalt concrete depend on the TI as shown in table 19.10. So here's the table 19.10. It is for the gravel equivalent factors for different types of materials. So let's move on to the structural design for Californian design method. So the objective of the design is to determine the total thickness of material required above the subgrade to carry the projected traffic load. This thickness is determined in terms of gravel equivalent GE in feet, which is given as GE is equals to 0.0032 TI times 100 minus R. So where GE is the thickness of material required above a given layer in terms of gravel equivalent in feet. TI is the traffic index. R is the resistance value of the supporting layer material, so normally determined at exudation pressure of 300 pounds square inches. So the actual depth of each layer can then be determined by dividing GE for that layer by the GE factor G sub F for the material used in the layer. So a check usually is made to ascertain that the thickness obtained is adequate for the expansion pressure requirements. Another general principle is the mechanistic empirical pavement design. So the mechanistic empirical pavement design, or MEPD, method uses empirical relationships between cumulative damage and pavement distress to determine the adequacy of pavement structure to carry the expected traffic load on the pavement. So it has a design procedure, 5 steps. So that design procedure consists of 3 stages incorporating the following basic steps. So step 1, select a trial design. Step 2, select the appropriate performance indicator criteria and design reliability level for the design. So step 3, we're going to obtain all inputs for the trial pavements structure under consideration. So step 4 is the evaluate the trial design, and the last step is to revise the trial design as needed. As for the 3-step procedure, we have this conceptual flowchart of 3-stage design analysis process for the MEPDG. So here is the conceptual flowchart of the 3-stage design or analysis process. So for computing the mechanistic empirical pavement design, we have some tables as well to compute the ESAL. So these tables, table 19.12, it is for the recommended design criteria or threshold values for flexible pavement, and the table 19.13 is the reliability level for different functional classification of the roadway. Just be guided accordingly with this table. So for the summary, so the design of the flexible pavement basically involves determining the strength characteristic of the materials of the pavement surface and underlying materials, and then determining the respective thicknesses of the sub-base, if any, base course, and pavement surface that should be placed over the native soil. So the pavement is therefore usually considered as a multi-layer elastic system. The thicknesses provided should be adequate to prevent excessive cracking and permanent deformation beyond certain limits. So these limits are considered in terms of required load characteristics, which can be determined as the number of repetitions of 18,000 pound single axle load the pavement is expected to carry during its design life, as in the AAHTO design method, or in terms of the number of repetition for a full axle load spectrum data for each axle type, as in the MEPDG design guide. So the design methods described in this chapter are the AAHTO design methods, which commonly are used by many state transportation agencies, the California design method, and the MEDPG design guide. So the MEPDG design guide is the most comprehensive design method, as in addition to factors considered by the other methods. It also provides the opportunity for the designer to be fully involved in the design process with the flexibility to consider different materials and design options. Although the design steps involved in the AASHTO and HBEM methods will be carried out manually, it is highly unlikely that the MEPDG can be carried out manually. The MEPDG method therefore is described briefly to guide the reader a general understanding of the design process. That's all. Thank you for listening.